It's my pleasure to be here at the Math Department to give a talk on abstract dynamic programming and reinforcement learning. I've taught a reinforcement learning class at ASU for the last 7 years, and I've written several books in the process, which you see here. Well, this one, Abstract Dynamic Programming, is the 3rd edition, was first written in 2013. All of these books can be found online, and also online, there's a 5-video lecture series on abstract dynamic programming, which focuses more on the mathematics of the subject. I will try to summarize this talk and also the field itself in one figure. I view reinforcement learning as the art and science of approximately solving optimal sequential decision problems. Now, dynamic programming also deals with optimal sequential decision-making. So reinforcement learning and dynamic programming try to solve exactly the same problem. However, the key word here is approximate. Reinforcement learning focuses on approximations, and there are two objects that that are important in dynamic programming. One is value functions or cost functions, optimal cost functions. And the other one is policies. We try to find an optimal or approximately optimal policy. And this leads to a natural bifurcation of the field into two strands, one based on approximation in value space, where we try to approximate value functions, and the other approximation in policy space, where we're trying to approximate policies. And these two have different principles and different methodologies. Approximation in value space is more closely connected with dynamic programming and also abstract dynamic programming, the subject I'm going to talk about today. And also has a close connection with Newton's method. Newton's method for solving fixed point problems. I will argue that this is fundamental. On the other hand, approximation in policy space is more connected with nonlinear programming. It has its roots in dynamic programming as well, but it's more connected to nonlinear programming, in particular, gradient type of optimization and also random search. I'm going to spend most of my talk on this blue strand, and near the end, I'm going to give you a few slides on the red strand. So here is my outline. First, I'm going to talk about the mathematical structure of sequential decision-making, optimal sequential decision-making. Then how do we abstract that and formulate an abstract dynamic programming problem that captures the mathematical essence of sequential decision-making. Then I'm going to talk about algorithms, in particular, the methods of value and policy iteration. And then I'm going to go into reinforcement learning, talk about approximation in value space and the connection with Newton's method, and then talk about approximation in policy space, where we parameterize policies, we optimize with respect to parameters, and we do this with forms of gradient descent methods and also random search methods. So let me start with a simple deterministic optimal control problem as an illustration. Control problems generally involve a state and a control. The states are denoted here by xk. Xk is the state at time k. Uk is the control at time k, and it's supposed to satisfy some constraints. And there's a system equation that provides the next state as a function of the current state and the current control. And there's a cost associated with each stage, g's of xk and uk. And we want to find a sequence of controls that minimizes over an infinite horizon here. There are finite horizon versions of the problem, but I'm going to, just for the purpose of illustration, I'm going to focus on infinite horizon. And these stage costs are discounted with an alpha parameter between 0 and 1. And I also assume for this example that G is bounded. These assumptions are needed to induce a favorable mathematical structure of this problem, a contraction structure. However, this example can be generalized to the case where there's no discount factor, G is unbounded, and so on. As to give you an idea, here's a classical control problem. Keep the state of the system close to a planned trajectory. Like a self-driving car wants to go from point A to point B and has to map out a route that respects the constraints, obstacles, velocity constraints, acceleration constraints, and so on, and try to stay close to that route. So here's the state is a four-dimensional, two-dimensional position, two-dimensional velocity, and the control are various acceleration controls. So I'm going to use this problem here to illustrate how we pass into an abstract description. So in dynamic programming, we use policies. We introduce policies that are functions of the state. Each mu k is a function from state to control. And once you have such a policy, it's a lookup table that gives you the control to apply at state x and time k. So ideally, you'd like to have those stored in a lookup table or generate them as you need. And when you are at state k at time k, you pick up the control and you apply it. So that's a policy. And if you have a policy, it has a cost function associated with it, the cost that you incur using that policy, which is obtained by plugging into the cost function this function's mu k under the assumption that successive states are generated according to this equation. So a policy has a cost function, has a cost associated with it, and this cost is a function of the initial state, x0. So it's important to know that this is not a number, it is a function, okay, a function of the state. Now, the optimal cost starting from state x is obtained by minimizing overall policies pi. This j stars of x, the optimal cost function, is the key object in dynamic programming, and it satisfies a fundamental equation, Bellman's equation. This is a functional equation. It has a solution. It's an equation over functions, and it has a solution j star. So this is a pointwise equation. It holds for every x. And if you look at the structure, it involves minimization of the cost at the current state plus an optimal cost to go from the next state and appropriately discounted with alpha. If you look at it more closely, it's a very intuitive equation. And the proof of it is also very simple. This cost of a policy can be written like so, as the sum of two terms, by breaking down the policy into the first function and then the remaining functions. And you write it like so. The pi1 function comes over here. So you minimize over pi on the left-hand side, minimize on the right with this pair over this pair, take pi1 inside the minimization, and there it comes, okay? It's a short proof, and there are similar proofs of Bellman's equation, perhaps more complicated. Generally, Bellman's equation holds in just about every dynamic programming problem. It took me like 40 years to discover a counterexample. There is a counterexample, but it's extremely difficult to construct. So you can take it as given that Bellman's equation is satisfied. Now, if you look at this Bellman equation, you see that J star is a fixed point of a certain mapping, T, that maps J functions into Tj functions, okay? So solving Bellman's equation is equivalent to finding a fixed point of this mapping. And for the example that I gave earlier, where G is bounded and it's a discount factor, it turns out that T is a contraction mapping with respect to the sup norm over the space of bounded functions J, and therefore J star is the unique fixed point of T by a classical theorem. So now let's do the same thing for policies. In dynamic programming, stationary policies are important. In other words, policies where the mu k does not change over time. So that's characterized by a single function mu. And the cost functions are denoted by j's of mu. So j's of mu of such a stationary policy starting at initial state x0 is given by this expression where xk is generated by a simple system equation. So you plug in this mu function into the cost function, plug it into the system equation, and you obtain, again, a function of the initial state, this J mu. And from the definition of J mu, you have this formula here, just breaking this down to the sum into the first term plus the remainder. So from this equation here, you see that J mu is again a fixed point of a mapping T mu given by this expression here. For a fixed mu, T mu of J is a mapping of J, and J mu is a fixed point of this mapping. So we have these mappings, T and T mu, and fixed point properties that are relevant. And you can also see that the T mapping and the T mu mappings are related by minimization, and that T is the lower envelope of the mappings T mu. Now, the mappings T mu are linear, as you can see here. So each one of those it has a graph that's represented by a line, many lines, and if you take the lower envelope of all those, you get the T mapping, which is, in this particular case, concave, has concave components. So here's a figure representing graphically the Bellman equations, J mu equals T mu of J mu, and J star equals Tj star, which is the lower envelope of the T mus. So for a given mu, okay, this figure is oversimplified. On the horizontal, we have J, and J is a scalar function. There's only one state here, actually, and J is a scalar, okay? And I showed here on the horizontal. And T mu has a graph that's linear, so it's a line. And its fixed point is obtained by intersecting the line with the 45-degree line, and at the intersection, you get J's of mu. So this is T mu, various T mus here, okay? And you obtain their cost functions by intersection with the 45-degree line and projecting down the horizontal, and you get this fixed point. Now, the T mapping is the lower envelope of the T mus, so it's a concave mapping. It's this red curve. This graph is this red curve that you see here. And its fixed point is over here at the intersection of the 45-degree line, projecting down. This is the solution of the Bellman equation, J star, J mu, J star. J mu obviously lies to the right of J star. So that's a figure to which we're going to come back again. And notice that you can also obtain the optimal policy from this figure. If you go at J star and look at all of those lines and take the minimum, you obtain this tangent line, which corresponds to the optimal policy. Now, if the red mapping were differentiable, this tangent would be the gradient, right? But it does not have to be differentiable. But in case it's concave, it's a subgradient. And this is a point to remember for later, because Newton's method is going to be defined in terms of this mapping. And the way you know Newton's method from calculus is for differentiable problems. But in fact, there's an extension of Newton's method to non-differentiable problems. And this is the one that's going to be relevant here. Okay. Are there any questions, by the way? Yes.
So if the time horizon is finite and you don't introduce the discount often, would you have a similar Bellman equation?
Yeah, you would have a similar Bellman equation, but it's not going to be a contraction necessarily, and it may not be defined for parts of J. It may go off to infinity. The theory of abstract dynamic programming allows functions that can take extended real value functions, can take the values plus infinity and minus infinity. So all of this is covered. And I will argue that it's also very general because the state space and the control space are arbitrary here. Okay, anything goes. That's an important fact about dynamic programming. If you develop things, you can develop things in a general way, in a way that applies to many, many different problems. And in fact, that's the point that I want to make here in the next slide, that there are other problems that involve stochastic structure, or minimax game structure. And for stochastic problems, the system equation involves randomness, a random variable wk in addition to state and control. And the cost function, the cost per stage also depends on wk. And now this is not a number anymore, but it's a random variable because of the presence of w. So to obtain the number to minimize over, you take the expected value of that, okay? So that's the formulation of the problem. And in minimax problems, it's similar, except that the WKs, the disturbance, is chosen from a set by some antagonist. And the minimization is done against the worst possible choices of the antagonist. So the structure is kind of similar, a little bit more complicated, but with an analysis that, that has been known since the 50s. You can show that J star, the optimal cost function, and the cost function of stationary policies are fixed points of mappings T and T mu. And this is the mapping T, involves the expected value over W, and T mu for a stationary policy, you just plug in, instead of the minimizing U, you plug in the mu value, okay? So this is for stochastic problems. And for minimax problems, instead of expectation, you use maximization. And by the way, the lower envelope property still holds. T is the minimum of the T mu's. And so a lot of the structure that I gave in the previous slide is preserved. So now let's come to abstraction. All of these problems have similar structure in terms of the Bellman equation. So we're going to abstract the ideas involved in a way that we can deal with a unified analysis. Okay, abstraction in mathematics. I found this quotation from Wikipedia, which I like. I'm not going to make you read this, but I'm going to just summarize it. Abstraction is extracting the underlying essence of the mathematical concept, generalizing so that it has wider applications. We don't look at applications, we look at the basic mathematical structure. And the advantages are that it reveals deep connections between different areas of mathematics. Known results in one area can suggest conjectures in a related area. Techniques and methods from one area can be applied to prove results in a related area. All of this is very relevant to the ideas that I'm going to present. But the essence is eliminate the clutter and let the fundamentals stand out. That's the approach. So what's fundamentally dynamic programming? After you get a little bit of familiarity with the field, you figure out that the most fundamental thing is the Bellman equation operator. So the idea is, in place of specific Bellman operators specific to different problems, introduce an abstract mapping, H, that depends on state, control, and function, cost function. And then introduce a Bellman equation that has this form, minimization over U, and introduce also a Bellman equation that corresponds to policies, which you plug in here. So for the deterministic optimal control problem, H has this form that I gave earlier. For the stochastic optimal control problem, it has this structure here that I gave earlier. And it involves expectation. For the minimax problem also has a similar structure with maximization in place of expectation. There are many other dynamic programming problems, semi-Markov decision-making, exponential risk-sensitive cost functions, affine monotonic. There are many different types of dynamic programming problems, and they can all, and each one of them has its own function H. So the key premise here is that H is the mathematical signature of the problem. It captures all the important data about the problem. And it's sufficient to operate on this, to investigate on the basis of this H to obtain general properties that apply across the board to other problems. So we'll adopt a top-down development, start from an abstract view, and then do analysis and develop computational methods at the abstract setting, and then specialize to various problems, deterministic, stochastic, minimax, exponential, what have you. So that's where we're aiming. And here are the specifics. We introduce a state space X and a control space X. These are arbitrary. A control constraint that involves choices that depend on, that are constrained by the current value of X, stationary policies, mapping from state to control, satisfying the constraint. And we introduce a mapping H from X, U, and the space of extended real valued functions, which are monotone. That's a key property. In dynamic programming, you have this property which says that if you take J and increase it uniformly, then H of J also increases uniformly. If you look at dynamic programming, all the dynamic programming problems that you can come up with have this monotonicity property. And so we assume that, and it turns out to be an important property. Introduce a lot of structure, regardless of whether you have contraction or not. So for each policy, we define the mapping T mu, like so, as you would expect. And you also define T, the mapping T, by minimization over the T mu's. Again, you have the lower envelope property. And we introduce the problem now. We introduce the mappings, but now let's introduce the problem. The cost function of a policy is obtained by taking the limit of this expression here. And J bar is some function. For example, J bar equal to 0. And if you look at this expression, it represents the cost over a finite number of stages using this policy. Stages from 0 to n as a function of the initial state. So this expression for the cost of the policy is the limit of the finite horizon cost of the policy as the horizon goes to infinity, okay? Okay, so this is a composition, mathematical composition of mappings T mu 0 up to T mu n. So T mu n minus 1 operates on T mu n J bar, and going backwards, it's a dynamic programming process actually, you obtain the finite horizon cost starting at state X and with terminal cost J bar. And if you take the limit of this, you obtain the cost of a policy. And the optimal cost function is obtained by this minimization, and we're aiming at an optimal policy, one that attains the minimum. Okay, how about time varying policies? Well, in dynamic programming, most infinite horizon problems have a stationary optimal policy. So this is not overly restrictive to have to look at stationary policies, even though the problem definition involves time varying policies. Okay, so the optimal cost interpretation is what I mentioned earlier. This expression here is the cost of starting at x0 using pi for n stages and incurring terminal cost j bars of xn. And the theory revolves around fixed point properties of the mappings T mu and T. Typically, Bellman's equations holds, and the minimization in here gives you an optimal policy. This is an optimality condition. The algorithms for finding J mu and J star are extensions of the classical dynamic programming algorithms of value and policy iteration, and they're special cases of fixed point algorithms. So I'm going to come into that. So that's our problem formulation with T mu and T defined in terms of the abstract mapping H. Okay. So now there's several types of abstract dynamic programming problems that depend on the structure. One is the contractive model, where all these T mu mappings are contractions. It's patterned after the discounted optimal control problem with bounded cost per stage. And these T mu mappings are subnorm contractions or weighted subnorm contractions in some case. a representative problem of the contractive class is the one that involves a finite number of states, finite number of controls, a discount factor. This problem has a contractive structure. T and T mu are contraction mappings. And this is by far the most commonly used model in reinforcement learning. It's the easiest one, the one where nothing goes wrong, okay? On the other hand, whether it's truly the best formulation to use is in a given practical situation is debatable, although in reinforcement learning, people tend to use this without looking at the details. Okay, so this is the model for reinforcement learning. And in my opinion, it has received undue emphasis. There are other problems that are just as interesting, both from the point of view of theory and practice. The name for these is MDP, Markovian decision problems. Another type of problem that has less structure is one that the monotone increasing and decreasing model that is patterned after the non-positive and non-negative cost undiscounted dynamic programming problems. These are important classes of models that also allow for an infinite state and control space. They are very appropriate for classical control theory type of problems. And the analysis of these has no reliance on contraction properties, just based on the monotonicity of T mu and T. All of these models have a long history, starting from the 50s. It's an important paper by DeNardo in 1967. The monotone increasing and decreasing models are from the 70s. And this is my paper here. And also, they are treated quite extensively in my stochastic optimal control book with Stephen Shreve that appeared in 1978, a monograph. There's another class which is a focal point of my recent work, my abstract dynamic programming book and its subsequent editions since 2013. And these are semi-contractive models. And these are patterned after control problems with a goal state, a termination state, or a destination state. Here, the structure is that some policies are well-behaved, like contractive, and others are not. So now the analysis becomes more complicated. It turns out, however, there's substantial and very interesting theory, in my opinion, associated with these models. And from the point of view of applications, this is a common model in dynamic programming under the name of stochastic shortest path problems. This type of problems are represented with shortest path problems where you have a destination that you want to reach at a certain time. And there's no discount factors don't make sense in this context. So it's a different structure. Some policies are constructive, some other policies are not contractive. And in reinforcement learning literature, they have also received a lot of attention under the name episodic MDP. An episode is a trajectory of the system that reaches the termination state. So MDP and episodic MDP, or more mathematically, contractive and semi-contractive. So now let me discuss algorithms in abstract dynamic programming. These are patterned after the value iteration and policy iteration algorithms, and they are also fixed point algorithms. Value iteration. This is the classical fixed point iteration in mathematical numerical analysis. And here we have again J, T sub J, the Bellman operator in red. We want to find its fixed point, intersection of the 45-degree line. And we start from some function, some initial condition. We calculate J0, calculate T sub J0, reflect around the horizontal, Tj0, then T squared J0, then T cubed J0, and so on. And all of this converges if you have a contraction, but converges also in other cases where you don't have a contraction to the fixed point, which lies over here. So it's a very fundamental method in dynamic programming and relates to a classical fixed point iteration. We iterate over values, value iteration. Now, another important method in dynamic programming is policy iteration, where you iterate over policies. Here you start with a policy and generate a new policy with improved cost. Starting policy, mu 0. Next policy, mu 1. The next policy of the next policy is mu 2, and so on. And here's the process. Okay, J in the horizontal, the Bellman operator in red. The starting policy has a graph that's a line, right? And the fixed point of that is gives you the cost function of that policy. Now, this operation is called policy evaluation in dynamic programming. So you have a policy, you evaluate it, and then you improve it. You get a better policy with lower cost. And how do you do that? By minimization in the Bellman operator over policies. You get a T mu 1, and graphically, out of all these lines is the one that comes closest to this point here. We look at this vertical, we look at all the lines and their intersection with this vertical, and then we go as low as possible. And you can see that we come down to the point where the line becomes a tangent. Oops, sorry. Becomes a tangent at this point. This line corresponds to the new policy, which is in reinforcement learning parlance, this is called the rollout policy, base policy, a rollout policy. Now, when you evaluate this rollout policy, you have to intersect this line with the 45-degree line, and you get this point. So the cost function of the rollout policy is this one. Base policy here and rollout policy here. And you can see that this step here is a Newton step. A Newton step for solving this Bellman equation. Why is the Newton step? Well, what do you do in Newton's method? You're at the current iterate, you linearize the mapping at that iterate, and you solve the linearized problem, and that's your next iterate. That's exactly what we do here. We have this iterate at J mu 0. We linearize the red mapping at this iterate, and then the linearized problem is to find the intersection of this line with the 45-degree line. And that's the next policy. That's exactly Newton's method. The only thing is that this may not be differentiable, maybe piecewise linear, for example, but then things work out by using subgradients and supporting hyperplanes and things like that. So that's policy iteration. It's a basic method, both for reinforcement learning and for, obviously, dynamic programming. And the connection with Newton's method here, if you do multiple iterations, you're going to obtain the full-fledged Newton's method, not just a single Newton step. Okay, so now I'm going to go into reinforcement learning. And first, approximation in value space and Newton's method, how it manifests itself in the context of reinforcement learning. So approximation in value space in reinforcement learning is a very simple idea. We replace the optimal cost function, which we don't know, it's very expensive to compute. We replace it with an approximation J tilde in Bellman's equation. So in place of J star here, we use a J tilde and we minimize, and that's how we obtain a control at state X online. So this expression here represents the first step cost starting from state X, plus the cost of the future stages as evaluated by J tilde. We minimize overall U, and that gives us some minimizing control at state X. And if you piece together all of these controls, you obtain a policy, right? A mapping from state into control. So this defines a look-ahead policy, a one-step look-ahead policy, mu tilde, with mu tildes of X being the minimizing U in this expression. And there's a critical mapping here. You plug in something approximate, and you obtain an approximately optimal control. how are the approximation errors related? So from a cost approximation J tilde, we obtain a cost function of the one-step look-ahead policy, and an approximation error, J tilde to J star, gives you a performance error, suboptimal policy cost over optimal cost. So what's this? This is a critical mapping, and how can we understand that? Before I get into this, let me also note that there's a multi-step look-ahead version of this approximation value space, where instead of looking at the first step and then approximating the future, we minimize over the first L steps and then look into the future as approximated with the function J tilde. So that's how L step look-ahead approximation value space works. At a given state, we solve an L step problem involving the controls from time 1 to time L. We find the optimal sequence, and then we use the first element in the sequence. And then we go to the next state, and then there we repeat the process. All of this is done online. Once you have J tilde, you can generate these controls online. So the key question is, what's the relation between J mu tilde and J tilde? And the answer for this is simple. It's a Newton step relation. J mu tilde is obtained from J tilde by means of a Newton step for solving the Bellman equation fixed point problem. A second interesting question is, do we gain something out of multi-step look ahead? This is a more difficult minimization than this one. And how does multi-step look ahead affect the critical mapping? And we're going to see that multi-step look ahead helps in a particular way. So I want to explain this with a figure again. This is a principal focus of my books and also my course. It's a very simple idea, but I want to make the point that without abstract dynamic programming, without an abstract view, it's unlikely to see this. For me, it took like, I don't know, maybe 40 years. It's just if you play around with this and have a framework that thinks, a mental framework that's based on abstraction, then you can see things like that. Otherwise, they're invisible, in my opinion. So here's the explanation of the Newton step. Remember that we start with a cost approximation, and we want to find the cost function of the one-step look-ahead policy. So how do we find this one-step look-ahead policy? We look at all the lines that intersect this vertical, and we come to the lowest point. This gives you a line that's tangent to the graph of the Bellman operator. And then the cost function of that policy is precisely at the intersection with a 45-degree line, and it's this point here. So what do we do to get from J tilde to J nu tilde? Well, it's a Newton step. We linearize the red mapping at J tilde, solve the linearized problem, and there it is. So that's the Newton step. And the effect of this is obviously very, very important, because Newton's method, even a single Newton step, has a superlinear convergence. If you're close enough to J star, then J mu tilde is almost optimal. And you see that in reinforcement learning. There's plenty of computational evidence. On the other hand, if you start far away from J star, then this Newton step may not be effective because you may be outside the region of convergence of Newton's method. All of this is very well known from calculus, and it generalizes to the case where the operator is not differentiable. So let's look at L step look ahead. Now there's an important point to notice here, that L step look ahead is not really much different than one step look ahead. It's just one step look ahead with a different J tilde. J tilde is replaced by J tilde after it's operated on with T L minus 1 times. So you start with J tilde, apply value iterations, L minus 1 value iterations, and then apply the Newton step. So that's the graphical representation of L step look ahead. Start with a cost function approximation J tilde, perform a number of value iterations, 3 of those in this particular case. I'm sorry, 2 of those in this particular case. And then use this T squared J tilde as the starting point for the Newton step. So it is a Newton step at the end of some first order iterations, or in, as they call it in numerical analysis, a Newton SOR. SOR stands for successive over relaxation. So it is a Newton SOR step instead of a Newton step. And an important point is that these first order iterations, the value iterations, bring the starting point for the Newton step closer to the region of convergence and closer to J star. That's the role of multi-step look ahead. It improves the starting point for the Newton step. Note also that only the first step of the look ahead is a Newton step, and the remainder serves to enhance the starting point. So that's the key interpretation, and there are a lot of different variations of this this methodology. But let me also discuss the implications of it. And I think the key implication is that the critical relation between cost approximation and policy performance errors, this relationship is superlinear because of the Newton step, as long as you are within the region of convergence of Newton's method. So there is some region here near the optimum where the even substantial approximation errors make hardly any difference on the performance error. On the other hand, there's another region here where the error of the performance error is catastrophically large. And this is the curve for one step look ahead, and there's another curve for L step look ahead. So this has far-reaching implications for both theory and practice, and it has been verified. This performance relation has been verified with many studies. There's a stability threshold that is defined by the region of convergence of Newton's method. And given a certain approximation architecture for J tilde, for example, like a neural network, this defines more or less the general region within which you operate. If you have a good approximation architecture, you start over here. If you have a bad approximation architecture, not a very powerful one, then you start over here. And then if you start in here, even if you try to improve it, the approximation by using better training, more data, doesn't have much of an effect. If you are within the region of convergence of Newton's method of the Newton step, you're almost optimal as you zoom in one iteration. On the other hand, if your approximation architecture is not very powerful, and you start out somewhere over here, and then you try to improve it by collecting more data, training better, and so on, it's not going to help you because you're going to be outside the region of convergence of Newton's method, and things are going to turn out not well. So this figure redefines the name of the game, what you should be doing in order to have success. And one major factor for success, which certainly helps, is increase the length of the look ahead so that you obtain a curve that's better. And if you want to think intuitively about this, think of chess, okay? Chess involves multi-step look ahead with cost function approximation. The way you make a chess engine better is by increasing the look ahead. And that's a manifestation of this phenomenon here. So are there any questions? Yes?
Is there a relation between the L step look ahead and the condition number of the Hessian that's involved in the enumeration?
There's no Hessian here. The mapping is typically non-differentiable. In fact, okay, if you look at the previous figure, okay, here it's differentiable, but if you look at this figure, it's non-differentiable. In fact, it's piecewise linear. For a piecewise linear mapping, the Newton step is exact. There's no approximation if you start close enough to J star. So in particular, if J tilde is within this segment here, okay, and here the segment is quite large, then you're going to converge in a single step. So there's no notion of convergence rates, condition number, because it's a different game. And a lot of the things that we know from numerical analysis about Newton's method do not apply. Any other questions? Of course, there are some problems where there is a Hessian. And these are, for example, linear quadratic problems, not control, have a differential cost function, and other problems. But the difficulty is that we can't figure out what this Hessian is. It's just a game that's very difficult to get anything out of. So I don't know of any results, to be concrete. I don't know of any results where a condition number analysis has been applied to this context. Okay, as I mentioned, there are several variations of this methodology, like approximations of policy evaluation, simulation-based ideas, truncation of the simulation, truncation of the horizon. And there's also an interesting variation that involves a double Newton step. Think of having an initial policy, think of having an initial approximation, calculate a one-step look-ahead policy, and then obtain the rollout policy based on that, and that gives you a second Newton step. So first Newton step, second Newton step, and this is the overall effect of the two steps. Now, interestingly, the first major success story of reinforcement learning comes from the 90s with a backgammon program by Tesoro, program called TD Gammon. And this was the AlphaZero of the 90s, okay? A very major development, was very impressive and very motivating. And it was based on a double Newton step. You can interpret this in terms of a double Newton step. And there have been other experiments involving double Newton step and even triple Newton step, but and you get a lot better performance, as you might expect. And this has been very helpful. I just want to illustrate here that there are a number of different variations, and a lot of insight can be obtained through figures like this. Okay, so I have a few more slides on approximation in policy space. Remember, there's a bifurcation in reinforcement learning between approximation in value space, which what I've talked about so far, and optimization in policy space, where what we do is we parameterize the policies, and then we optimize the parameter to obtain an optimal policy within the parameterized class. And the way we do this is typically with methods that are based on gradient type of ideas, okay? I call them, the name that you see is gradient descent. It's a misnomer because even though it uses gradient, it doesn't involve descent. It's not a descent method. Sometimes people use the name stochastic gradient descent, but they may not be stochastic at all. In fact, typically they are deterministic. You get a data set, and then after that it becomes deterministic. You may use stochastic methods to obtain your data set, but once you have the data set, it's a deterministic gradient method. So, however, there is a connection with stochastic gradient methods that have been applied in the context of approximation in the context of stochastic algorithms, going back all the way to the 60s, perhaps, or 50s. So let me describe these methods. I'll use the name incremental gradient methods. And these are the workhorse of machine learning. Most machine learning algorithms use this type of method. And they apply to a particular problem, minimizing a sum of terms, fi, the cost function f of y is the optimization variable, is the sum of many, many terms. And fi of y typically represent the error between the ith data point and a model y. Y represents a model within the class that you're trying to, within the context of the problem you're interested in. And you collect a lot of data. Each data point corresponds to a little function like that. And this expression typically represents the error between, the whole expression quantifies how well the model matches the data. Okay, it's a very classical problem. And we assume here that each fi is a differentiable scalar function of y. Now, the ordinary gradient method, the one that goes way back to Cauchy, perhaps, is one whereby from the current iterate yk, you obtain the next iterate by moving in the direction of the negative gradient. You evaluate the negative gradient of the current iterate, and you go at the negative direction, along the negative direction by a step size gamma k, right? Now, if you look at the gradient of this function, it is the sum of the little gradients, right? Now, these gradients correspond to data points, and you may have thousands of data points or millions of data points. So this gradient is very, very difficult to compute. It's very costly to compute. So here's the idea of the incremental gradient method. Instead of using this entire sum of gradients, just pick a single gradient, a single data point from here, and go in the direction of the negative gradient for that particular data point, ik. Now, the computation from here to here is like night and day. It's a huge improvement. And that's what makes these methods work. They're very cheap. And people have been very inventive about improving these methods. For example, there are practical methods used very widely in neural network training, for instance, that use diagonal scaling here. The idea of diagonal scaling is a very, very old idea in nonlinear programming and in gradient methods to improve the condition number of the problem. And people in reinforcement learning and machine learning have been very inventive to find ways to compute good scaling factors online. There's a method called ADAM, okay, which is used a lot these days. It involves diagonal scaling, and it has poor convergence properties. That's another dichotomy between theory and practice. The new methods, the ones that work in this field, have very poor theoretical support. They are not convergent in general, but they may converge on your problem, and that's what's important. By hook or by crook, by using heuristics, by changing various parameters, they may work on your problem, and they may work very well indeed. Okay, there is a way to explain the advantage of using why these methods work. There's a graphical interpretation here goes way back. That's the one that I understood this methods using this figure, actually. And you may look at this figure later, but I'll briefly try to explain it. Suppose that you have to optimize a sum of quadratic functions. So these component functions, the fi's, are these here. And we want to minimize the sum. So the minima of these quadratic functions are in a range from the maximum to the minimum. And the true minimum of the sum that you would like to find lies somewhere in here. Now, so this is the problem with a scalar y. And suppose that you start further out to the right. And instead of using the entire gradient involving the sum of the gradients of this cost function, you just pick one of these functions and you move in the direction of the negative gradient of that. Then no matter which one you choose, if you're far out to the right, you're going to be moving in the right direction, a lot more cheaply than otherwise. Similarly, if you start from the left, you're going to be moving in the right direction. So When you're far from convergence, the incremental method, gradient method, is as fast as the ordinary gradient method, but only for a fraction of the work, okay? On the other hand, when you're close to convergence, when you get inside this region, then you may be picking the wrong function, and you may be confused, oscillating back and forth because you don't know exactly whether the true optimum lies to the left or to the right, and so on. So I call this the region of confusion. And the way to remedy this is within the region of confusion to diminish the step size with an appropriate rate so as to make the method converge. It's possible to do that. On the other hand, people in the neural network community, they don't do that. They just perhaps reduce the step size a little bit, but very often in machine learning, it doesn't matter to get the exact optimum. All you need is get within the region, get somewhere close to the optimum, and that's good enough. So I think that's the mental picture that I at least have in mind about these incremental methods. Okay, now let's go to the reinforcement learning context of policy optimization, approximation policy space. We introduce a parametric class of policies where there's a parameter R that parameterizes the policy. Each one of these R's defines a stationary policy, which I denote by mu tildes of R, possibly randomized, and it has a cost. Once you plug in this policy, it has a cost starting from a given initial state. And okay, so this policy observes the current state, knows the current parameter, applies control, and all of this is evolves over an infinite horizon and generates a cost, and this is the cost that you see here. And now we optimize overall parameters within the parametric class. We minimize this expression. Hopefully this one has a gradient. Hopefully you can use some kind of a gradient method. And there's also a generalization where you, instead of optimizing for a fixed initial state, you optimize with respect to a probability distribution of states. And very often these evaluations of cost function and gradient involves data, collecting data. So this has the nature of a sum of components, which brings into play incremental gradient methods. So these methods have had very substantial success, very important successes, particularly recently. You heard about DeepSeek, right? And it's trained using methods like this, okay? So these are important methods from a practical point of view. On the other hand, from the optimization theoretical point of view, they will freak you out. They freak out me. This problem is just horrendously difficult, and these gradient methods, the way they are applied, they are just don't make much sense to an optimizer. And let me give you an example of this. It's my last slide. The pitfalls of policy optimization. Here is the simplest dynamic programming problem that you can possibly think of. It has two states, left and right. And the cost for moving from left to right is 2, moving from right to left is 2, staying it's 1, and staying here is 0. So the optimal policy is to try to get to the right state, which has 0 cost, and just stay there, okay? So if you parameterize these policies with a parameter R, the optimum, okay, this R is now the probability of moving from left to right. One of the difficulties here is that these Markovian decision problems have a discrete control space. So the gradients cannot be defined unless you consider randomized policies, which involve probability distributions that have continuous character. So that's what we do here. We introduce a probability a randomized policy. R is the probability of moving from left to right, and 1 minus R, the complementary probability, and similarly here. Now, the optimal policy involves two parameters: what you do when you are at left or what you do when you are at right. But here we have compressed the policy space into a single parameter, R. And now look what happens. If you look at this figure here, I'm showing the cost function corresponding to a policy for the value R, okay? So R equals 1 is over here and corresponds to the optimal policy, where you move always to the state R. And R equals 0 is at the other end, corresponds to doing the opposite, moving to the, staying at left and moving to the left. Now, the optimum, of course, is this one here. And this is the cost function as a function of R. It's a scalar cost function. And it's concave. It's not convex as you would like, it's concave. And it has two minima. One is optimal and the other is the worst possible, okay? So what's going to happen if you apply a gradient method here? If you start closer to, it will converge to the closest minimum from where you start. If you start somewhere over here, it's going to converge to the suboptimal minimum. And if you start on this side, it's going to converge to the optimum. But the situation is actually worse when you're using data. When you're using data, these gradient directions are computed with errors, stochastic errors. So it's possible to start over here, move towards this good point for a while, and then through the lack of the draw, you may jump over on the other region and go back and forth. And you never know whether you're going to converge to a true minimum or to something that's worse or far worse. This is observed in practice, by the way. People apply these methods by trying many, many starting points. They try different random seeds into the generation. Each random seed may give you a different convergence point, which may be good or may be bad. So my view is that these methods are not really gradient methods in the classical sense. They're a combination of gradient methods and random search. You search randomly among the starting points or among the simulation runs that you do, and then you pick the best point. And the gradient optimization does something or tries to do something to enhance the random search. You pick a random point and then you try to do some gradient steps. Maybe they will work, maybe they will not work, but they generally tend to give you an improvement. And then you collect all these zillions of runs from different starting points, and hopefully with trickery and heuristics, you can arrive at a good solution for your problem. It's not going to work for everybody's problem, but may work for your problem, and that's maybe all that you need. So that's the unfortunate state of policy optimization. Obviously, it's not to my taste or to a mathematician's taste, I may say, but that's reality. These methods have had tremendous success, and yet they are a mathematician's nightmare, in my opinion. And that's what you have to live with in the context of reinforcement learning. So that's my talk. Thank you.
Any questions?
So when you're doing the iterated gradient method, and you're in the region of confusion, what's the value in increasing step size to get better convergence if you're going to be possibly converging with the wrong?
You use a step size that goes down according to harmonic sequence, a 1/k sequence, roughly speaking.
But what's the value in increasing your convergence likelihood? Like, are you And when you get in that region, are you considering more of the component quadratics?
Well, for
step?
quadratics, of course, it's easy to predict what's happening. But if you have a general cost function that has multiple local minima, who knows, okay?
Right. So you could be converging very quickly, but to the wrong one.
You could be converging very quickly to the wrong one, or you may be oscillating around a good one, or you may be oscillating around a bad one.
There's no way.
There's no way to tell. Yeah.
So it's very interesting that you brought up the TD backgammon algorithm and then put in this perspective. I wonder, in general, when dealing with such a policy decision-making problem with randomness, do you usually use the expectation or use the worst scenario? In particular, TD backgammon, I don't know.
In backgammon, well, it is a two-player game, so it's a minimax type of situation. You have to optimize against the worst possible play of the opponent. But this is not explicitly done in the backgammon. You assume the way the TD gammon program works, you start with a certain policy and you use that for both players simultaneously. And then you try to improve on this policy, but simultaneously for both players. Now, this is not rigorous. In fact, there have been counterexamples where feeding a lookalike of AlphaGo, okay, which is trained again by using a common policy for both players, and people have been able to beat AlphaGo by finding out vulnerabilities in the training method. On the other hand, there's another possibility. In fact, Yuchao and I have worked on that, on using, in a min-max situation, use in place of the adversary, the actual opponent, use some kind of hypothesized nominal opponent, a good opponent, like in chess, for example, where we have applied this idea. Instead of using a min-max framework where there's a maximizing player that tries to find the best possible move in response to our move, use an engine, a good engine that picks moves for the arbitrary. And then we optimize against that engine. That makes the training process much faster. And surprisingly, we have obtained very, very good results. But the inside of this is complicated, and I can't really explain it. I can explain it later offline. But I think this is a promising approach. Instead of using a true adversary, substitute some good adversary that you optimize against. And then it becomes a one-player situation. You can apply all your tricks in approximation value space, or even approximation in policy space, and converge to a local minimum.